In case we don't actually complete this experiment in the classroom, this video is going to run through Unit 3, Part 2, Lesson number 3. And this is our practice with graphing exponentials and logarithms using the sensors attached to our calculators. So for this particular experiment, we're going to investigate graphs of the temperature of hot and cold water. The idea is that if we understand exponential and logarithmic functions, we should be able to determine the amount of time that it takes for water that's at an extreme temperature, either really hot or really cold, to approach an acceptable temperature. Think of coffee as it comes right out of a machine. It's often too hot to drink, and so we have to wait a certain amount of time before that cools off. Well, we can use this model to predict how long we actually have to wait. Now in the classroom, our TI Inspire calculators have a USB port on the top, and if you insert these different probes, in this case it's a temperature probe or a thermometer, it will automatically start a new document, and it's going to be set up for data collection immediately. Your TI Inspires that are installed on your computers will do the same thing. The USB ports are different, so you'll just need a probe that has a regular USB cable if you're plugging it into your computer like I am, or you would use the mini USB connection if you're plugging into the handheld calculator. So on my calculator here, this is the one that's in the computer. I need to change this rate to an interval. I don't want to take 2 samples per second. Instead, I want to change this to say I would only like a sample or a measurement taken every 20 seconds. So notice this is not samples per second anymore, but it's seconds per sample. So 20 seconds per sample taken. And so this is telling me that it'll take 10 measurements over a period of time. The period of time is 3 minutes or 180 seconds, and I'm fine with that. Right now I have a cup of water that's being heated up in a microwave, and we're going to start with it first. And while that's heating, I'm going to make note of the ambient air temperature. According to my thermometer right now, the air temperature in this room is 19.7 degrees Celsius. When the microwave is done heating this water, we're going to place the tip of the temp sensor into the cup and give it about 60 seconds for the sensor to acclimate to the hot water, and then we're going to report the temperature of that water. So the microwave is going to go off in a second. Maybe you can hear it in the background. I'm going to go ahead and put the temp sensor into the water. Okay, the thermometer is going into the water now. We can see the temperature change pretty quickly. And I'm going to give it about 60 seconds to acclimate. I'm going to pause the video and resume in just a few moments. Okay, it's been about 60 seconds, and you can see that the temperature's gotten quite warm. It's about 94 point some odd degrees. I must have hit a cold pocket there. About 93, 91. Let's wait till it levels off. About 93.1. Now in a moment I'm going to remove the thermometer and then press play on the computer screen to start recording data. And as soon as I remove this thermometer, that's the temperature that I'm going to record. So here we go. Okay, 92.2 was the temperature when I pressed the play button. So I'm going to let it run in the background, and on my notebook here I'm going to put 92.2 degrees Celsius. So we've removed the temperature probe from the hot water, and now we can make a prediction. I don't want to be looking at the calculator at this point, but we're going to make a prediction as what the graph looks like. Make sure to label your axis. So if this is time and temperature on your axis, what do you think the temperatures, or what's the graph going to look like? We had a data point way up here at about 92, and we know that the room temperature is down here at about 19.7. What's the graph going to look like? Is the temperature going to fall along a straight line? Does it form a curve? Does it slope down steeply at the end? Does it slope down steeply at the beginning? Make a guess. Go ahead and pause the video and resume playback in a moment. When we return, my data collection should be complete. Okay, the calculator is almost done. It's taken 9 measurements so far, and we've got the data points here. Time is about to run out, and there it is. There's our last data point that was collected. So hopefully you've got a sketch, or I'm sorry, hopefully you've got a graph that looks like this on your calculator. It may or may not match the sketch that you predicted. My initial guess was that it was a linear drop in temperature, and in reality we just didn't quite see that. So at the very bottom here, I'd like to copy the information from the calculator. And so to do that, I think we can switch over to this key here. This will show us our table view of the data. And we can now read the temperature at every interval. So I'm just going to start copying that over. At time 0, it was 91.2 degrees. So not 92.2, but 91.2. That's okay. We don't need to make the change. Then it dropped to 63.4, and so on. I'm going to take a moment to copy this data now. Now, if you had just a regular thermometer and a partner to do this with, you could have built this table ahead of time, and your partner could have been reading a stopwatch, and every 20 seconds could have told you to record the temperature, or at least call out the temperature. So at the beginning you might say 91.2, and then at the 20-second mark you can call out this temperature, and so on. So you don't really need the TI Inspire to do this experiment. It just is making it pretty nice because you can do it with one person. So what I would like to do is also plot these data points. I'm going to create a scale on my X and Y axis, and I'm actually going to plot these data points. So I'm going to just eliminate this asymptote here. I'm going to leave my guess in place, but for now I'm going to take a few moments to actually enter this data onto my guess. So before I plot my points, here's the scale that I settled on. I selected this scale because it seems to fit the X and Y axis pretty well. Our temperature runs up to 90 degrees and we've got a little bit more room, and then our time runs from 0 up to at least 180. You'll notice that when I labeled these, I marked each hash mark vertically in increments of 10, but I only labeled them every other hash mark, which is fine. And same thing on the horizontal axis. I labeled these hash marks every 3 grid lines to indicate every 20 seconds, but I only labeled them every other. And that's a perfectly fine method as well. And here's what the sketch would look like now that I've plotted all of my data points. Again, each of the Y coordinates was established based on the thermometer reading. The X coordinates were the time that passed. Now this is kind of interesting to me because I know that the room temperature is 19.7 degrees, almost 20 degrees Celsius. So the graph should be leveling off towards this number here, and based on the data that I've collected so far, it almost doesn't look like that's happening. So we may have to kind of interpret this and see what's going on there. Maybe it is just slowly dropping, and maybe eventually it will level off towards that number. Maybe it'll just take longer than we thought. I do know that the boiling temperature for water is about 100 degrees, or is 100 degrees Celsius, and I'm not a fan of drinking coffee that's that hot. If it's 100 degrees Celsius, I don't think that would be very comfortable. Different people have different pain thresholds, however, so when the temperature drops to 50 degrees, that might be appropriate. When the temperature drops to 60 degrees, that might be appropriate. Some people might prefer to wait till the temperature drops to 35 degrees. Well, each one of those temperatures correlate to a different x value on the x-axis, and we would have to solve for x based on the equation that generates this curve. We will generate that equation a little bit later in this worksheet. Let's run the same experiment, only this time we're going to start with cold water. We're going to fill our cup with ice and cold water, And we're going to make note of the ambient air temperature. And before I go do that new experiment, I'm actually saving this document. These inspires give us the ability to save the work. So I don't know if the data is going to be preserved if we move on to another set of recordings. So I'm just going to save this now as temp hot. And now I'll create a new document. And if the thermometer doesn't bring up a new document right away, it's a vernier data quest that we're working on right now. So it looks like the thermometer has acclimated to room temperature again. This time it's reading 19.9 degrees Celsius. And the next thing we're going to do is place the tip of the sensor into cold water, and we're going to give about 60 seconds for that temperature to acclimate. Okay, so I've placed that thermometer into the cold water right now. It's cooling off. I didn't have any ice cubes, so this is just cold water from the refrigerator. We'll see how cool it gets. This time it looked like it settled on its temperature pretty quickly, and that should make sense to you. If you think about it, the air temperature was about 20 degrees, and it's looking like this water temperature is just a little bit below 8. So it didn't have as far to change. There wasn't that much temperature differential in order to see the difference here. So in a second I'm going to press the record or play button here to start the recording. Although before I do that I need to check this. The settings were changed. So the interval is 20 seconds per sample. And the temperature is about 7.7. We again know the temperature of the room is somewhere up here, and the temperature of the probe is about 7. So what's your guess? What shape do you think the graph is going to create this time? Go ahead and make a guess right now and sketch that on your graph. And I'll start recording the data off screen. And while the data is collecting off screen, I went ahead and adjusted my scale here. I didn't make a guess as far as the shape goes, but my last guess wasn't too good, so I think this time the graph is going to follow an exponential curve as it heats up. So I know it started at around 7 degrees, so I'm going to say that it increases in temperature this way and then levels off as it gets closer to air temp, which is about 20 degrees. So this is the shape that I think it's going to produce. As I check in on the data, we're almost done. We've got 9 of the 10 data points collected, and time is almost up here. And there it goes. Okay, so this isn't quite the curve that I expected. It looks like it kind of increased pretty rapidly at the beginning, and then it decreased the rate of increase, if that makes sense, as time progressed. It made this more sweeping curve. So if we switch over to our data table, again, this table is something you could have done by hand if you had a partner recording the measurements with you, but since the calculator recorded this for us, then this is perfectly fine. So we've got this data that needs to be transferred into our table. I'll go ahead and do that now. And here are the results from the table on the calculator, now reported in the table on paper. Take a couple moments now and plot these data points onto your graph, please. So this scale wasn't all that great for the actual data. You know, my assumption was that we would approach this room temperature within the 3 minutes that it was outside of the water. That really didn't happen. The window of our scale existed between about 7.5 and 15. So again, from about 7.5 up to 15, that seems to be an appropriate range for the actual data. We just don't quite see the curve that occurred when the temperature was increasing. But again, I think that comes down to the fact that the temperature differential wasn't all that great. I mean, we only had about 12 degrees difference between the two here, as opposed to, you know, almost 70 degrees of difference here. So the change was a little bit more dramatic. So So because of that, I am going to switch my calculator back to the temperature hot document, and I'm going to go through this data analysis with it. We could also do the same for the cold temperature analysis, and I'll leave that for you to do as a challenge. And so here I am back on the home screen, and I'm going to open up the document. So I'm going to browse for it. And I did not put it in any specific folders, so here they are at the bottom of the pages here. You could create folders just like you would on a computer, but I didn't do that here. So I'm going to open up the file that contained our hot data. And here's that information. So now I'm going to follow the instructions on the handout. We're going to press Control then Dock to add a new page, and we're going to choose Data and Statistics. So Control Dock to create a new page, and we'll select option 5 for Data and Statistics. And so the data that popped up on the screen is all over the place. It's scattered all over the place, and that's because we haven't specified which variable should be placed along the x-axis and the y-axis. So if I activate the cursor and click along the bottom here, which one of these two should go along the x-axis? Well, hopefully you recognize that that's the time unit. According to our graph, the time unit was along our x-axis. And therefore, when we click along the y-axis, we would place the temperature. If you had switched those two and placed time on the y-axis, we'd have a graph that looks pretty similar, but it's not what we're after. And when we analyze this with the calculator, we're going to get a result that's not as meaningful. So let's make sure that we do have time along the x-axis and temperature along the y. By the way, when we switch the x and the y-axis, the input and the output, the domain and the range, we're essentially identifying inverse functions. So this is one way that the calculator can help us find an inverse function pretty quickly. So we're going to let the calculator find an exponential equation that fits this data. We're going to press the menu button, we're going to choose option 4, and then option 6, and we'll show the exponential option number 8. Menu, 4, try to do that again, number 6 for regression, and then we want option number 8, the exponential regression. So the calculator's done what it can to find the formula for an exponential equation, c times a to the x power, and it's performed an analysis on this and found that this line, this black line here, is as close as it can get to all of these data points. If that line was changed just slightly, then it'll be too far away from one data point, and therefore the fit wouldn't be as good. Now personally, I don't think that this fit is very good at all. I don't think that that black line strikes enough of the blue data points, and I don't think the curve is quite right. But this is the best that our calculator can do with how it's programmed. And so I've recorded the exponential equation here, and we've got a c value of 71 and an a value of 0.99. Does that c value seem appropriate? Why or why not? Take a moment and provide a response here. Does this number seem appropriate? If so, explain why. If not, explain why. Well, I would say no, this doesn't seem appropriate because the initial value, the starting point of this graph, was 92.2, not 71.2. And as we've discussed so far in this unit, the c value should be your initial value, the temperature in this case at time 0. Where was the temperature at time 0? Well, it wasn't at 71, it was up at 92, so I don't think that c value is appropriate. Now what about the a value, our growth factor or decay factor? Does 0.99 seem appropriate for it? Take a moment and respond, please. Resume playback in a moment to see what I would say. Now, without being influenced by the graph that we saw, I would argue that the a value does seem okay. It's hard for me to tell if it's perfect or not, but it seems okay to me because what I'm thinking of is that a growth factor of 0.99, since it's smaller than 1, since it's less than 1, that means that we're actually decaying. So our temperature is decaying here, which is correct. And a factor of 0.99, which is 99%, means that it's decaying 0.01 or 1% per unit of time, per second in this case. And so this seemed about right to me. When we pulled that thermometer out of the hot water, it was dropping at about 9 degrees per second at the beginning, I would guess, because it did drop significantly in that first 20 seconds. As the temperature got closer to, say, 30 degrees, then it would be dropping at about 3 degrees per second. And again, I think that was pretty close. It may not be perfect, but I didn't feel like it was too bad. Now, the fact of the matter remains that when we look at this particular graph, it doesn't fit well. And there are a couple things that we need to remember. A graph, or an exponential function that's in the form f of x equals c times a to the x power, this has a horizontal asymptote at 0. The graph will always tend towards 0. And if c is positive, we have a data point above the x-axis. And if a is less than 1, but still bigger than 0, then the graph will decay from left to right, and it will tend towards 0. What we need to keep in mind is that our room temperature was not 0. And so the graph should not tend towards 0. In fact, it is offset by the ambient temperature value V. And when we think of a sketch of the graph here, this room temperature is going to be the horizontal asymptote that we're after. And so we would want an initial value that's larger, some amount larger or higher than this horizontal asymptote. And that way the temperature of the thermometer could approach ambient temperature and level off more towards this horizontal asymptote rather than the origin. And so for that reason, we might have to challenge ourselves and see if we can do better than the calculator. We can make guesses and check our guesses for C, A, and B. If you're really up for a challenge, you can guess an H value, which is our horizontal shift we talked about in the end of last video. But let's start making a better guess here. I'm going to argue that the B value should be about 19.9 because, again, the room temperature was about 19.7, 19.9, 20 degrees Celsius, somewhere around there. So I'm going to make that guess for B. I'm going to place a C value at about 92 degrees because that's, again, about the temperature that we started at. And then I can just play around with guesses for the A value. And so if I switch back to the calculator, if I press the menu button and choose Analyze, which was option number 4, and then choose number 4 again for plot function, I can provide an equation that I think is a better guess. So I'm going to guess again 92.2 times, and I don't know, let's say a growth factor is 0.99. Let's say I was happy with that guess from before. 0.99 to the power of x, and add to that 20, because again, I think that's where the temperature was leveling off. Well, there's the graph that's presented by the data that I just used there, and that doesn't look too bad. The shape, anyway, is pretty good, but now I just realized something. This starting value, C, remember, that C value is the measurement of height above ambient temperature. And while this is 92 degrees in air temperature, this measurement was about 20 degrees. So the difference between the two, the change in the temperature, is really only about 72 degrees. So I'm going to go back and change that, and let's see how good it fits now. So again, menu, actions, plot function, number 4. Well, it won't let me edit that here. So I just press the escape key to make that disappear. Let's see, can I double click? Yeah, I can double click on the existing equation. So I'm going to change this from a 92.2 to a 72.2, and then I'll press enter. Now we're getting somewhere. The first data point and the last data point are pretty close, but the graph in between still doesn't quite fit. So since I would like for this to be a little bit steeper, I'm going to change the rate of decay. So I'm going to jump in here, and instead of calling it 9900, let's call it 999. Let's make it a little bit closer. Whoops. That was a 20. This one is supposed to be 999. That's just my next guess. It's supposed to be, or it could be a little bit closer to our original calculation. Whoops. That went in the wrong direction, didn't it? So let's fix that again. So 999 didn't work. Let's go smaller than 99, and we'll call it 0.90. And that's a little too steep. And so as I was typing on the screen with my pen here, the cursor was just kind of acting a little bit out of control. So I went ahead and just paused the video, and I started making some guesses here. I ended up feeling that 0.9890 was a pretty good growth factor here. And I did play around with an H value, and I settled on 20 because that shifted my graph. Now, just to make this stand out compared to the original function, I'm just going to press and hold my cursor on the equation here, and I'm going to choose option 5 and change this line color from black to something else that'll stand out slightly different. Let's go with blue. And now we can see how the original function was this black line here. I'll click on it so that we can see it again. And now we've settled on this blue function, which I still think we could have done a little bit better now that I see it again. I bet we could have made that a little bit steeper and so on. But I tried about 10 different options, and this is the one that I'm happy with for right now. But now we have an equation to work with. 72.2 times 0.989 to the x plus 20th power plus 20. And if I feel that this is the equation that's going to represent the temperature of that coffee as it's cooling off, I don't know that it's a really accurate measurement, but let's just assume that that is the formula that represents the temperature of the coffee. Let's suppose that I am the type of person that wants a 35-degree hot beverage, and I know that this equation will tell me the temperature as time passes. Do you think we can use our knowledge of exponential and logarithmic functions now to solve for x? We have everything else that we need. We just need to isolate the x value. I know this video is getting long, so I'm going to go ahead and wrap this up pretty quickly here, but I'd like to challenge you to solve for x too. Pause the video now and resume playback in a moment to check your work. And here's the work that I would show in order to solve for this solution. Now, pay attention here. I did not bother to find the result at each of these intermediate steps. I didn't want to use a calculator, and I didn't even want to do mental math until the very end. I'm just showing all of the algebraic steps, and I think this is a fine approach to solving some of our problems. I know that in order to isolate x, the first thing I have to do is subtract the 20, then I'll divide by 72.2, and then I'll rewrite the exponential as a logarithm. So I didn't bother trying to do that math ahead of time. I didn't bother to find out what 35 minus 20 is. I know that it's 15, but I didn't even bother writing that down. I don't know what 15 divided by 72.2 is, and it didn't bother me to not calculate it yet. I'll be able to put it all into the calculator one time at the end. But I have a number here on the left. This will calculate to be a number, which equals an exponential on the right. And since I don't know the power of x, I don't know how to solve for x here, I rewrote the exponential as a logarithm. The base of the exponential is the same base as the log. We evaluate this logarithm at this number over here, 35 minus 20 divided by 72. And I knew that that would be equal to the exponent as it sits here. Finally, we can subtract 20 from the result established here, and this would be a good no calculator answer. We could ask this complicated question without a calculator, and this would be a good result. The only time we need the calculator is to evaluate this expression, which I've done here. I've evaluated the logarithm based on the entire expression that was written, and we ended up with a result of 122.066. What this is telling me is that if the temperature of the coffee at the beginning was 72.2 degrees above that horizontal line, so about 92 degrees, then it takes 122 seconds in order for the temperature to settle out and reach 35 degrees. And that's pretty close to to what we saw over here. I think that's pretty close. At 120 seconds precisely, we were at 36 degrees. At 144 seconds, we were just below 34. So somewhere in between, at about 122 seconds, I think our temperature was about 35. So I think we've done a nice job. Hopefully you've been able to recreate this on your own and had similar results. If you've got questions, please let me know. Thanks for watching.